2, 1. Alright, welcome to another exciting video here for Math 2070. And today, as promised in the previous video, we will discuss matrix multiplication, or at least we'll begin the conversation. Okay, so let's set up some terminology. So we've already talked about matrices. We've seen how they appear as a way of representing systems of linear equations. Well, let's give a little bit more machinery around it. So when we say an n by m matrix, so n by m right there, we mean a matrix that has n rows and m columns. So rows first, columns second. And with that, we can then represent matrices as basically a collection of vectors that have been smushed together. So the columns would represent the vectors, and each entry in the vectors is corresponding to the rows. So for example, here is a 2 by 3 matrix A, consisting of the entries 1, 2, 3, 4, 5, and 6. And I can break this down as really just 3 vectors that have been put together. The vector A1, corresponding here to the vector 1, 4. The vector A2, which is the vector 2, 5. And the vector A3, which is the vector 3, 6. So again, note the number of rows. There are 2 of them, and that means that my elements are living in R2. Okay. So we've already seen matrices, and here we see another way of looking at them in terms of vectors. And last time we discussed how vectors play an important role when it comes to systems. So let's start setting that up. Now, given an n by m matrix, then I can take an element of Rm, and I'll define A times x to be the linear combination of the columns of A with the entries of x as the scalars. So here we see A times x is this linear combination of the vectors corresponding to the columns of the matrix, and the scalars being the entries of the vector x. Ooh, hey! Linear combination of vectors. We've seen that every system can be written as a linear combination of vectors. Oh boy. It's all coming together. Alright, but for an example, let's see this in action. Let's say I had a 3 by 2 matrix. Here we have 3 rows, 2 columns, and an element of R2. X defined as follows, and I wanted to do A times x, so following my rule, I take column 1, scale it by entry 1, column 2, scale it by entry 2, and combined. Simple as. Alright, now, that being said, we need to be paying attention to dimensions here. Here we had a 3 by 2 multiplying an element of R2. That's valid. However, a 3 by 2 multiplying an element of R3 can't happen, right? Because we got to take the column and scale. Well, this third one would correspond to a phantom third column that does not exist. Okay, so it's possible that A times x is undefined if you're not paying attention to your dimensions. Okay, so word of warning. Alright, now that being said, kind of already let the cat out of the bag where we're going with this, but A times x equals b is the same as this linear equation, where b is just some right-hand side, and here we've got our linear combo of the columns. Note that can basically just be written as the augmented matrix. In other words, the system of linear equations. So in other words, trying to determine the solutions to a linear system is the same thing as finding solutions to that matrix equation. So now we've got basically 3 ways of viewing the same thing. You have a collection of linear equations, and you're trying to find the values that will satisfy the system of equation. Or maybe you've got some vectors that you've scaled up and added and got equal to something. You're trying to figure out the scalars that work. And now I have a matrix A and a matrix B, and I'm trying to find the vector x so that A times x is equal to b. So in particular, here is this beautiful system of linear equations. Note 2 variables and 3 sets of equations, the number of variables corresponding to the number of columns we're going to have, and the number of equations corresponding to the number of rows. I can rewrite this as ax equals b, where a is the coefficients of... this is another crackhead example. What's going on here, man? This is two in a row where I've got my matrix all goofy. Alright, let me go ahead and fix that. The first row is wrong, as you can see. The 8 and the negative 2, that doesn't match up. This one's good, and that one's good, so I don't know what's going on with the top row. Beats me. Alright, anyway, there you go. Fixed. Beautiful. And here we see we've got our matrix, again corresponding to the coefficients here, now correctly corresponding to the coefficients. The vector x, an element of R2 corresponding to the unknown variables, and our right-hand side being our right-hand side. Beautiful. So, there we see that our system here can be converted over to our matrix equation. Nice, and we're interested in solving systems, and now we have another way of doing that by looking at a matrix equation. So in light of this new information, now that we're privy to the new information, it seems like that we should focus our efforts on studying the matrix equation AX equals B. Alright, now let's make that clear. Saying that that can be solved means we can find a vector x that satisfies it. So in other words, I can find scalars so that the linear combo of the columns equals B. And another way of saying that is that B belongs to the span of the columns of the matrix. Now this is the secret sauce. This is the real powerful stuff here, because following that previous point, if I give you some vectors out of Rm, I can make a matrix, an m by n matrix. Again, m here is representing the number of entries, so it's the rows. N, I have n of them, so how many columns I've got. That set is a spanning set precisely when the columns of our matrix span all of Rm. That can only happen if Ax equals B always has a solution. Ax equals B is the same thing as creating the augmented matrix AB, because it's the system associated with it. That means that if I can always find a solution, that means my augmented matrix cannot have a pivot column in the furthest right column for any choice of B, which means that the echelon form of that matrix cannot have a row of zeros, and thus A must have a pivot position in every single row. So, as we saw last time, if you want to determine something as a spanning set, it was pretty involved computation, but now we see, with the power of matrices under our belt, and matrix multiplication, Ax equals B, if I want to determine that I've got a spanning set, you just got to set up the matrix, find the echelon form, and then check for any rows of zeros. Because if there is a row of zeros, then in this augmented matrix, we can always rig it so that a pivot column appears in the rightmost column, thus guaranteeing we don't have a solution. So now, if you actually want to check for spanning set, it's actually easy. You take your vectors, smash them into a matrix, row reduce, get a row of zeros, you don't span. No row of zeros, you do. So for example, if I give you this list right here, 1, negative 4, negative 3 for our first vector, 3, 2, negative 2 for A2, 4, negative 6, negative 7. Here I have 3 elements of R3. Do these span or not? Well, we make our matrix, give it a little row reduction, and we find that in this echelon form I have a big fat row of zeros in the bottom. This is not a spanning set of R3. If it was, I would have to have 3 pivot columns, but here I see I only have 2 pivot columns. There we go. So last time when we checked if something was spanning or not, we had to go for a pretty long computation, and here we see we just get an echelon form and go, oh, I got a row of zeros, no span then. And similarly, if we were to modify what we had here, if we had 3 vectors in R2, and if I set up the matrix and get the echelon form, well then I see I have 2 pivot columns. No row of zeros? It does span R2. Now, of course, the spanning of R2 here might be a little redundant, because things may not be independent of each other, perhaps linearly. Ooh. That might be an idea we have to look into a little bit. But here we see that we now have a nice little method for detecting spanning without having to go through that computation we saw last time. That's quite nice. Alright, now, as a final point here, and this one's going to be a very powerful point, given a matrix A and vectors and scalars, it turns out that scaling and adding behave well with matrix multiplication, meaning that a matrix multiplying a sum of vectors is the sum of the product, and the matrix times a scaled vector is the scaled matrix times the vector. So, in other words, if we're looking at this and thinking about some things we've seen before, we might remember some stuff about calculus where the derivative was a linear operation, because the derivative of a sum is the sum of the derivatives, the derivative of a scaled function is the scaled derivative. Oh, and here we see matrix multiplication is also behaving like that. And note in particular, this means that any matrix times the zero vector must equal 0. And that's a pretty obvious, because if you were just think about what A times the zero vector would be, well, then you'd be scaling all the columns by 0. However, I like this little trick, and this is one that one of my friends in college pointed out to me. During office hours for linear algebra, we had a similar sort of thing we had to do, and I had this like really elaborate explanation for it. And then he basically went like, well, you have the zero vector, and the zero vector is 0 scaling 0, so you can just pull up, so then you just do that. So this little trick's always been a little favorite of mine. And it's in that similar vein of a lot of the dirty math tricks where you multiply by 1 or you add 0. Here's a multiply by 0 trick. Now, this little fact here is going to be very important and powerful for us, because now, note, this tells me that if I had a times x equals 0, well, I always have a solution. Ooh, don't tell nobody. Alright, so let's wrap things up today with a neat little thing. So, a n by n matrix whose columns are these standard basis elements, these vectors that we saw last time, we call that the identity matrix. So, for example, this is the 3 by 3 identity matrix by taking these and slapping them together, in the case of n equals 3. And in general, we'll denote this by a capital I, and if we care about the size, we'll include that in the notation, but for the most part, we'll just use bold I for the identity matrix, and the size of it will be clear from context, hopefully. Now, note something about this. If I multiply a vector by this, note that it needs to be the linear combination of these with the scalars, and we noted, hey, last time that this is a spanning set. In particular, the linear combination is just scaling by the entries. So, hey, matrix multiplication by the identity matrix doesn't do anything, hence its name. Ooh, that's pretty cool. All right, so we will probably push that a little bit further as we go towards some more matrix arithmetic. We'll see a little bit later. Alright, but for today, that's it for the matrix equation AX equals B. So we have now seen that every system can be rewritten in terms of AX equals B. We have seen some basic properties of this wonderful little equation. So naturally, we want to talk a little bit more about how do you go about solving this. And, well, let's see about that in the future. Alright, I'm out.